Exam 4. Well, so it's Wednesday the 19th. Yeah, the 19th, I mean. And the topics, I guess, are going to go up through rotating coordinate systems. Okay, and I'll answer questions today, as many questions as you want, I guess, and then when we run out of questions, I'll just go back to working on examples with rotating coordinate systems. So you have homework questions? Mm-hmm.
Yes. We have don't actually have a homework, but basically two different coordinate systems, one at the center and then one at the joint.
Yeah.
And I came up with two different.
The answers didn't match? Yeah. Okay, thanks. Okay, why don't I just do that one? Okay. Almost match or they did match? Good job. Okay, so you got the arm. Replace them. Thank you. Okay, so it specifies a coordinate system. I guess that's a pretty natural coordinate system, though. X, Y, like that. And yeah, so this is B, and this is A. And you're going to do it in both of those two coordinate systems. What do you know? The radius of the disk is 1.5 meters. The length of the rod is 1.3 meters. And the disk rotates about its center with an angular velocity of -5. That's going to be in the y direction. So 5 radians per second that way. And an angular acceleration of +10. So the angular acceleration is like this. And then the rod rotates about its hinge with a constant angular velocity of +8. That's about the z-axis, so that's like this. And we want to calculate the acceleration at this point here. Okay, so yeah, let's do it like Ryan said. We'll do it where we just have to deal with the rotating coordinate system. That's part B first. And then we'll do the deluxe model where you have to also deal with the fact that the origin's accelerating. I think the benefit of these problems is that it makes you be clear about the relation, besides reminding you that sometimes you have to deal with relative motion in addition to rotating coordinate system. It makes you be clear about the difference between the r vector and the p vector. And those are easy things to mix up, you know. So, B. Yeah. Yeah, it can be tricky. And sometimes you have that epiphany and then it goes away. Often it goes away late at night, I've found. So first we're going to use the coordinate system at B. So is the origin accelerating? No, so we don't have to use relative motion. Are the axes changing orientation? Yes, so we do have to use the equation for rotating coordinate system. We're trying to find acceleration, right? Okay, so the acceleration of P is equal to, let's think of this as the acceleration of P that's observed plus capital Omega dot cross P plus 2 times capital Omega crossed with the velocity of P that's observed plus capital Omega cross quantity capital Omega cross P. So we have the two ways of writing these equations. How do I choose whether I'm going to write it in this form or whether I'm going to do it with the components dot? They mean the same thing, but what's the distinction I'm making on those? Yep.
If you have a means to find the acceleration velocity, it's easier to do it this way. But if you just have a position vector, time can
yeah.
Something you don't want to do.
I mean, that's the right idea. I think the way I would describe it is, if that rotating coordinate system is giving you like a position or a velocity as a function of time, you just have a way to take those derivatives of those components. And that's when you use, the components dotted. But if you just have information like this, I don't have any function information at all. All I have is a snapshot of information at this instant. And at this instant, I'm always just using these things because I'm going to use the circular motion equations to find these observed velocity and acceleration. Okay. All right, so now we just have to find all these values. Well, in this coordinate system, how do we calculate the velocity of P that's observed in the coordinate system? So in other words, you can always think of it as now stop the base rotation, the horse rotation. Now the horse is just standing there watching the motion of the cowboy. So you just have a camera here that's watching this arm, go this way. Okay. And so that's just circular motion. And circular motion to get a velocity that's lowercase omega crossed with the position vector, the r vector. Dang it. The r vector. Thank you. So omega is going this way. That's a positive angular velocity about the z-axis. So that's 0, 0, what was it, 8? And what's the definition of the r vector? Yeah, from the center of the circular motion to the point that you care about. So the r vector goes from A to P. That's just 1.3 in the y direction. So that's 0, 1.3, 0. And the cross product set is 8 times negative what? Negative 10.400. And then same idea for the acceleration. This is the watermelon equation. So alpha cross r plus omega cross quantity omega cross r. There's no angular acceleration of the arm. That's a constant angular velocity. And so we just have 008 crossed with 008 cross 1.30. We already calculated that, so that's this. And what do you get for that? Okay. Now, we're done using the circular motion, assuming that the disk is fixed. Now we're dealing with the terms that include the rotation of the disk. The angular velocity of the disk is negative 5 as a y component. So 0, negative 5, 0. And capital omega dot is positive 10 in the y direction. And then the only thing we still need is the position vector. At this instant, what's the position vector of P? Yep. So that's the key thing. Like, there's the distinction between R and P. This arm is just in a circular motion around A, right? So the R vector is just from A to there. But a position vector is always from the origin of the coordinate system. And so you have to go 1.5 in the negative x direction and then 1.3 in the positive y direction. And if you forget to do that, that'll, that's probably the most common reason you can't make these answers match up. So position is negative 1.5, positive 1.3. And now, plug and chug, the most glorious words in the engineering lexicon. So we have 0, negative 83.2, 0, plus 0, 10, 0. Yeah. A sub P. Crossed with negative 1.5, positive 1.3, 0, plus 2 times 0, negative 5, 0, crossed with negative 10.4, 0, 0, plus 0, negative 5, 0, cross quantity 0, negative 5, 0, crossed with the position vector negative 1.5, 1.3, 0. Yep.
A mark just appeared on the screen by the P.
Oh yeah, that's not a negative, thank you.
Yeah.
Anybody have this answer?
Yeah, it's 37.5 in the X, negative 83.2 in the Y, and negative 89.
Okay, good. That's an acceleration, so that's meters per second squared. For part B, R and P are different. Okay, so now part A. Is the origin, okay, so now we're done with this coordinate system at B, we're moving over to this coordinate system at A. The fixed point in this problem is B. Nothing else is fixed. So is that origin at A accelerating? Yes, and so we're going to have to use relative motion in this. And then, are the axes changing orientation? Yep. Okay. Yep. It's, yeah. So, relative motion. We're going to have to use the acceleration of P relative to the ground, which is what we want, is the acceleration of P relative to A plus the acceleration of A relative to the ground. This is just circular motion of A. This, in order to calculate the acceleration of P relative to A, we're going to have to use the rotating coordinate system equation. But terms are going to change. Well, I think the...
Is that rotation not part? No, it's not.
It can't be, right. I think the only thing that's going to change is that the our P vector is going to change. And then the differences that are made by changing that P vector are going to be made up for in this relative motion. So, okay, let's first calculate the acceleration of A relative to G. That's just circular motion of that point A. So that's alpha cross R plus omega cross quantity omega cross R. Yep. Yeah, I have an example like that. Yes. Okay, so what we're talking about now is the rotation of this point A. It's in circular motion around B. So our alpha vector is the angular acceleration of the disk. That's 10 in the positive y direction. So that's 0, 10, 0. And then our angular velocity is 0, negative 5, 0. And it's the r vector. So it's going from the center of the circular motion, that fixed point, to the point we care about, which is, in this case, the origin. So negative 1.500. If anyone has any questions, just please yell out in frustration. Yeah, sure. I mean, just something to get my attention, and then we can, from there, we can refine. So negative 1.500. Okay, so the acceleration of A relative to G is 0, 10, 0, crossed with negative 1.500 plus 0, negative 1.50, crossed with the quantity 0, negative 0.5, and negative 50, crossed with negative 1.500. Okay, anybody have that program in their calculator? Okay, what are the answers for that? Okay. Oh, okay. Yep, there you go. And now we'll go on to now we're going to go on to the part that you would get if this origin wasn't accelerating. So imagine that origin stopped, but the coordinate system was still changing orientation at the same rate. So now it's just sitting here going like this. Okay. And we're going to calculate the acceleration of P. So the acceleration of P relative to A is equal to the acceleration of P that's observed plus capital Omega dot cross P plus 2 times capital Omega cross the observed velocity of P plus capital Omega cross quantity capital Omega cross P. So let's figure out what all these are, and then we're just going to plug them in. Well, now our coordinate system is the one at A. So what's the position vector of P? Yeah, so now P is just 0, 1.30. The velocity vector is omega cross r, and our omega was positive 8 in the z. Our r vector stays the same because the location of the center of that circular motion doesn't change based on just the origin changing. So now we have 0, 1.30. This time r and p are the same vector. And the acceleration vector is alpha cross r plus omega cross quantity omega cross r. This is 0. And so we have 0, 0, 8 crossed with, what did we get for this? Is that 10.4?
Same value.
Okay, yeah, that's right. Negative 10.400. And what was that? 83.2 negative. Okay, so this is the velocity of p that's observed and the acceleration of p that's observed. The angular velocity of the coordinate system is 5 in the negative y, and the angular acceleration is positive 10 in y. So capital omega is 0, negative 5, 0. Capital omega dot is 0, positive 10, 0. And now we're ready to roll, right? So the acceleration of p relative to a is 0, negative 83.20, plus 0, 10, 0, crossed with 0, 1.30, plus 2 times 0, negative 5, 0, crossed with the observed velocity, negative 10.400, plus 0, negative 5, 0, cross quantity 0, negative 5, 0, cross p, that's 0, 1.30. Okay, well, this one goes away because you're taking a cross product of parallel vectors. This one goes away because you're taking a cross product of parallel vectors. And so what do you get for your final acceleration of p relative to a? Okay, and then finally you put those two together. The acceleration of p relative to the ground is equal to the acceleration of p relative to a plus the acceleration of a relative to the ground. That's 0, negative 83.2, negative 104, plus whatever we got at the beginning. Nope. 37.5015. And that's 37.5, negative 83.2, negative 89. They match. Isn't that like the coolest thing you've ever seen in your life? Yeah, the origin thing. You just forgot the origin thing. I mentioned this once before. Hey, welcome. That's what. This is like what your Tennessee grandpa would say when he asked about this. I got a question for you. Why come when you been making this big deal about how the time derivative of a vector in a rotating coordinate system is equal to the components dot plus omega cross the vector? It's the main point of this whole topic. But then, when you talk about capital omega dot, you just take the derivatives of the components. Yeah. I know. Oh, Grandpa. Your mom like rolls her eyes like, Grandpa. This is very rudimentary to the way rotating coordinate systems work. Basically, what your grandpa is asking in his down-home manner is, how come we can just say that? You know, the whole idea of this topic is that we know that U dot is equal to the components dot plus capital Omega cross the vector. What's the deal with that? Because, yes, Omega dot, if you wrote it out fully, so there's no contradiction. You can think of capital Omega dot as equal to the components dot plus this crossed with the original vector, but a vector crossed with itself is 0. Because the vector that we're taking the time derivative of in this case is capital Omega. Okay? And yeah. So when we're doing this calculation, I sort of gloss over that fact, and when we go to, we have the term that says capital Omega dot, and where is it? Capital Omega dot, and I just very blithely treat this as components dot, but it's because that second term just is 0. Any questions about that problem? Let's do another one like that. Okay. Wouldn't it be funny if you were like, I have a general question. Why don't we take that hill, soldiers? That's what would make it so funny. I don't know. Like, that's a question like a general would ask, you know. So it's like a general question. Okay.
Really cleared up for me. I was saying basically it's just to differentiate like kind of what one is dependent on which.
Yeah.
But I hate that analogy.
Okay.
Because the cowboy is stationary. He's not doing a motion. So maybe
in what case?
In that like if you in the analogy.
Okay.
But maybe he's a ballerina. You know what I mean? Like a ballerina on a horse. So
I see. I see what you mean.
Okay. So the question is kind of specific. Oh yeah. So, yeah, that's my life.
Yeah. So if you ever do watch, I mean, just if you do watch a rodeo, like think of like a bucking bronco, the cowboy is not stationary. Okay, yeah, that's a good one.
In the example of the rod and the disc, so we had the rod and then the disc. The rod is like this.
Yeah.
Do they have, so like if the rod is spinning and the disc isn't spinning yet, do they have the same acceleration?
The rod is spinning.
If the horse is spinning.
Yeah.
And the cowboy hasn't started.
Mm-hmm.
They have the same acceleration?
Well, they have different R vectors, so they'll have different accelerations based on that. Okay.
Sorry, say the last part you just said.
Well, if that, like in the problem we just did, if there was no angular velocity of 8, now that's just a rigid body.
Yeah.
And so you could just calculate that as a circular motion of this point P around this, just using the watermelon equation. It's just that now your R vector goes all the way from here to here.
Oh, okay. So you were
Wrong. Oh.
I was wrong. No. Okay. Make sure I ask all questions. Someone else have a question?
Yeah, anyone else have any questions? Yes.
So just curious, if we say took out the angular velocity and just had, say, a weight force on it, that wouldn't move because that weight force isn't producing any angular velocity or acceleration.
So we said that at this instant there's no.
We know if you were rotating that disk,
Yeah.
it would end up falling over.
Okay, so remember when we did. When we were first talking about circular motion, we first did it as kinematics. And then we went and we would have done kinetics problems where this thing is a linkage. Okay, so you'd have to do this as a linkage problem. Well, all of our linkage problems have been in 2D. And so we can't do that problem. I'm still sort of thinking about what to do in the last couple weeks. We might do rigid bodies in 3 dimensions. Just talk about it briefly, which would give you a way that you could. So doing rigid bodies in 3 dimensions is surprisingly complicated, but it would give you a set of steps where then you could go to 3D linkage problems if you wanted to try to think through it.
I guess 500 Newton force at that point would be something that would produce an angular acceleration. Could you just do that entire bar as a 2D problem, calculate the angular velocity / acceleration, and then use that in the problem?
No.
Okay.
Yeah, it gets pretty messy.
Okay.
Any other questions? Yes. Homework question. Homework problem. Yeah, which one? Okay. I got it.
Yeah, I got 2%.
Oh, well, now you're ahead. That's good. Okay, so 7. Okay, so now you guys don't have to do this one.
We should do it. No, because you're outside.
Yeah. Okay, so. I know this isn't like super satisfying because I know there's a test in a week and whatnot, but almost everybody is at this stage probably fairly confused. You know, there's a lot of confused thoughts about this. So it's not just you if you're, you know what I mean? This is complicated stuff to think through, and just little by little, you're just trying to like iron out one problem after another. You know what I mean? Yeah. 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 I believe you might be one of a few people who do, but that's the exception, not the rule. Me? I perfect is pretty strong, but yeah, I mean, yeah, it's eventually it all sort of can gel. Um, okay, so the 3-meter bar rotates with an angular velocity of, okay, so let me number these. So this is 1 and this is 2. Okay.
I'm sorry, a really basic question.
Yeah.
So we've got a lot of terms that sound
Yeah.
let's say, right, so W is angular velocity of the body. Delta fish is angular velocity or angular acceleration of the body.
Mm-hmm.
Capital omega is the angular
That's
velocity of the CX.
alpha fish. Yeah, that's an alpha.
Alpha. Did I say omega?
You said delta.
Alpha.
Okay. It looks like a goldfish. It looks like a Jesus fish. Yeah, right. Lower cases are always referring to a rigid body relative to a coordinate system. And uppercase are always referring to a coordinate system. Right. Okay, so the angular velocity, I'm going to call it little omega 1. This is the angular velocity of body 1, is 0, 2, 0. And that's constant, I guess, yes. And then for body 2, in this coordinate system, you have an angular velocity of negative 4, 0, 0, and an angular acceleration of 0, 10, 0. And we want to calculate the acceleration of p. And this one doesn't have a part A and a part B, but if you're looking for, as you're getting ready for the test and you're looking for extra problems to do, if you want to make sure you understand stuff, you can always move the coordinate system to another point and calculate it that way, and the answers have to match. So you can always sort of make problems to check yourself with. Yep. Yeah. I mean, the whole idea of these kind of problems is that you have two simple motions, so you're going to fix the coordinate system to one of those simple motions. And so because of that, your uppercase values are all going to be simple. They're all going to relate to the horse. The coordinate system is always fixed to the horse. Right, so is the origin accelerating? No, that's good. That's good news. Are the axes rotating? Yes. So that means the equation is going to be the acceleration of p is equal to the acceleration of p that's observed plus omega dot cross P plus 2 times omega cross the velocity of P that's observed plus omega cross quantity omega cross E. Let's see, we're pretty much out of time, but what's the position vector? Positive 3x, negative 2y. The velocity vector of P that's observed is not the circular motion, and we're going to use the angular velocity. So now we're imagining that one is fixed and just thinking of the circular motion of P around its joint. And so that's going to be angular velocity of body 2 crossed with the r vector. What's the r vector for P? 0, 0, negative 2, 0. Because you're going from the center of the circular motion to the point. So negative 4, 0, 0, crossed with 0, negative 2, 0. And you get 0, 0, 8. And then the acceleration of P that's observed is alpha 2 cross 0, negative 2, 0 plus omega 2 cross quantity omega 2 cross 0, negative 2, 0. I think I'll stop there. We can finish this on Friday. Yes. Yeah. Mm-hmm. Okay, so it's accelerating. That doesn't make any sense. Okay, what's 10? You're right. It would be like that. Must just be a typo. I mean, it has to be in the x direction. Yeah, that's a really good question. Why don't you can do this problem mathematically just with the way I have it drawn. That's impossible. You could design something that was capable of doing that, but it couldn't be just a simple pin joint like that. So if you're listening to me right now, you can change that to 10, 0, 0. If you're not listening to me right now, the math will work out the way it's written, and either one is fine with me. Okay.